So thank you very much for the introduction and the invitation. I mean, it's a great pleasure to be speaking here at this symposium in honor of Piotr. We know each other since way back. Okay, so the topic of this talk is initial data on Big Bang singularities. And my motivation for taking an interest in this topic is the desire to understand the structure of Big Bang singularities. Now, if you want to discuss the structure of Big Bang singularities, it's very hard to avoid a fundamental proposal that comes from the physics literature. And so this is the BKL proposal, which is due to Belinsky, Kalatnikov, and Lifshitz. And so very roughly speaking, the idea of this proposal is that cosmological singularities are space-like, local, and oscillatory. Okay, so what does this mean? So space-like means, maybe I can draw a toy picture here. So very naively, you should have in mind that there is a Big Bang at t equals 0. And if you have sort of observers going into the Big Bang, they will typically lose the ability to communicate as you go towards the Big Bang. And this is the idea that the singularity is space-like. There's also the idea that the singularity should be local, meaning that kinetic terms are more important than potential terms. Very roughly speaking, time derivatives are more important than space derivatives. So you throw out the spatial derivatives. And so each of these observers sees an evolution which is like an ODE. So each observer, sort of the dynamics are described by one ODE, one for each spatial point. That's sort of a local behavior. And then in the end, it should be oscillatory. So the model for this behavior is the so-called mixed master universe, which is a chaotic dynamical system, effectively. So you have infinitely many chaotic dynamical systems going into the singularity, right? So it's a bit of a mess. Now, there are some situations, though, in which, okay, let's see. Okay, so for some matter models, and also in certain symmetry situations, the oscillations are expected to be suppressed. And so you don't have this chaotic dynamics, rather the dynamics are convergent in some sense. I will become more specific in a moment. And this is more sort of, it's easier to handle mathematically. I'm going to, in this talk, be mainly interested in this quiescent setting. So that's the setting I'm interested in here. Right? So now this is in the physics literature, and there are many people who have been trying to make this perspective more precise, right? Mathematically precise. There have been many attempts to make it more precise. It's rather difficult. So one of these attempts goes back to the work of Erdely, Liang, and Sachs, on the one hand, and then to Eisenberg and Moncrief on the other hand. And so they introduced the notion of an asymptotically velocity term dominated singularity and velocity term dominated equations, right? So they introduced these notions. And again, the idea is a little bit like in the BKL picture, that you write the equations in some form, and then you just drop certain spatial derivatives, and then you get some model equation, this velocity term dominated equation. And the hope then is that if you take solutions to Einstein's equations, they should asymptote to solutions to these simplified systems, the velocity term dominated equations. That's the hope, right? Now, in order to prove that in all generality, that can be expected to be very difficult. So you can't really expect to hope to do that. But there is a simpler problem you could consider, and that is, well, let's say that we start with a solution to the simplified system. We start with a solution to the velocity term dominated equations, and then we ask the question, can we find a corresponding solution to the full equations that converges to this solution to the simplified system, right? So this is a simplified question you can ask. And this question actually Lars Andersson and Alan Rendell, they asked themselves this question. It's already almost 30 years ago. So they took an interest in the Einstein scalar field equations and in the Einstein stiff fluid equations. So these are particular matter models. And they were interested in 3+1 dimensions. And so, so their starting point is, let's assume that we are given a solution to this simplified system, this velocity term dominated equations, where you drop certain spatial derivatives. So we're given a solution to the simplified system. Can we then find a solution to the actual equations asymptoting to this? So the assumptions here, as you are given a real analytic solution to the velocity term dominated equations. I'm going to flash these equations in a moment, show them to you in a moment. And they're expressing the equations with respect to a so-called Gaussian foliation. So this means you have, so you're foliating your spacetime by constant t hypersurfaces. And then, so that it's a Gaussian foliation means that the d by dt vector field is perpendicular to the leaves of the foliation, and the squared length of the d by dt vector field is -1, right? Okay, so that's a Gaussian foliation. And also in their background solution, t equals 0 represents then the singularity. Okay, and now, so this is they have this background solution, right? So this is the starting point. But it's not enough to assume that you have this background solution. You also have to make this assumption. So we're given a solution to this velocity term dominated equations, but that's not quite enough. You have to assume a little bit more. And the additional assumption you need to make is what I've written here, that tk is positive definite. So what is tk? Well, so k here is the so-called Weingarten map of the leaves of this foliation, right? So you have the intrinsic geometry, and then you have the extrinsic geometry. The extrinsic geometry is represented by the second fundamental form, or alternatively, the Weingarten map. It's, if you would like to think of the second fundamental form as a covariant two-tensor field, the Weingarten map, you just raise one index with the induced metric, or I mean, it's a shape operator, or what you prefer. But anyway, this is describing the extrinsic geometry. And it turns out for the velocity term dominated equations, this quantity is actually constant, right? So not for Einstein's equations, but for the velocity term dominated equations, this is constant. And the assumption now is that this 1,1 tensor field, it has to be positive definite, right? So that's a requirement that they're making, in addition to having a solution to this simplified system, right? And what are the conclusions they're getting? Well, the conclusions they're getting is that, well, if you're given this model solution, then there is a unique solution to the full system of equations that is asymptoting to the given solution to the model equation, right? And they're very specific asymptotics I'm not going to go into, right? They're some rather technical conditions here, right? So this is a corroboration of the BKL proposal, in the sense that, well, if you start with a solution to the simplified system, there is a unique solution to the full system asymptoting to the simplified system, right? So that's nice. But you can also view this result in a different way. You can say that, well, you can think of this solution to the velocity term dominated equations as initial data on the singularity, in a sense, right? So you can think of them, this solution to the simplified system, this is data on the singularity, and given data on the singularity, there is a corresponding solution to Einstein's equations. That's another way to see it. And this result was then later generalized to higher dimensions and lots of different matter models, still in the real analytic setting. So all of these results are in the real analytic setting, and there are no symmetries, right? And real analyticity is not so natural a setting for Einstein's equations, as I don't know if Piotr will say something about this, but so anyway, so this is one example of results where you sort of, in some sense, put data on the singularity. In the absence of symmetries, there are lots and lots of other results in the presence of symmetries. So I'm not going to go through all these results. So these are some examples. And in this case, the formulation is slightly different. So here, you're sort of, you effectively prescribe the asymptotics of some metric components in these settings, right? So the asymptotic data in this case is that you have an asymptotic expansion of symmetric components, and the functions appearing in those asymptotic expansions, these are effectively the data on the singularity, and then you prove that there is a corresponding solution, right? I'm going to give an example of this in a moment. And then there was a little bit of a renaissance with Paul Klinger, who was, I believe, a student of yours, no? Yeah. Yeah. And so anyway, so he proved a similar result in the absence of symmetries for Einstein's vacuum equations in 3+1 dimensions. And this should surprise you, because what I said in the beginning, so the BKL picture, you expect solutions to the vacuum equations to be oscillatory, right? But it turns out that if you turn off a certain degree of freedom, you can get this sort of convergent behavior even for Einstein's vacuum equations in 3+1 dimensions. And that's what he did. This was again in the real analytic setting, and this was later generalized or upgraded to a result in the smooth setting by Fulmov, and Luke. And this is rather important that you get this result in the smooth setting. They also, I think, removed some restrictions here. Okay, so these are some examples of sort of results where you put data on the singularity and then you get a corresponding solution. And I'm just going to give you a flavor of what this data look like. So if you look at what are the velocity term dominated equations, I'm just flashing them here. I'm not so that you remember, just so you get a flavor. So it's this and this, right? So this is the solution to these are the velocity term dominated equations. And so in practice, you've taken Einstein's equations, you express them with respect to a Gaussian foliation, like I was explaining here, and you drop some of the terms, right? But there are still some spatial derivatives here, so it's perhaps slightly mysterious. Then this is how it looks. I mean, just to give you a vague feeling for how it works. This is how it looks in a case with symmetries. So in this case, the asymptotic data are these four functions. So you have four functions corresponding to an asymptotic expansion of these two, Z and X, which are functions that appear in the metric somehow, right? So the data on the singularity in this case are, describe the asymptotic expansion of symmetric components. That's another notion of data on the singularity. And this is now Fulmov and Luke. So in this case, the data is this, there are some functions on the 3 torus, right? And given these functions on the 3 torus satisfying various conditions that I written down here, so these are the conditions, then there is a corresponding solution to the Einstein vacuum equation. So this is just to illustrate that there are lots of different notions of data on the singularity. But the relation between these different notions of data is not so clear somehow, right? At least not to me. And so what I want to propose here is yet another notion of data on the singularity in the hope of trying to find a sort of unifying perspective on these things, right? And so in the last few years, I've been trying to get a more geometric picture on the mechanisms close to the singularity. And now I'm going to try to explain another notion. And so to do that, I need to explain to you what is the matter model I'm interested in, first of all. So I'm going to be interested in the Einstein nonlinear scalar field equations. So in this case, the matter model is fixed once you fix a potential, and a potential is just a smooth function from the real numbers to the real numbers. And once you fix that, then everything is fixed. So then you have Einstein's equations, which is G equals T. So here G is the Einstein tensor, so it's the Ricci tensor minus the half times the scalar curvature times the metric. And T is the stress energy tensor, like this. So it's Einstein's equation. And then the scalar field has to satisfy this, right? So these are the equations I'm interested in. And I mean, you can use this to model, I suppose, inflation close to the Big Bang. You can use it to model dark energy at late times. But I suppose I mainly think of this as a toy model here somehow for this setting, right? Okay, and now I'm interested in trying to get perhaps a little bit more geometric picture of what's happening as you go towards the Big Bang, right? In order to describe this a little bit more geometric picture as you go towards the Big Bang, I need to sort of describe the setup, right? I've sort of, well, pictorially, it's rather similar to what I've drawn here. So I'm thinking I have a space-time, so it's a manifold with a Lorentz metric, right? And then I'm assuming that it has some nice foliation. So I have a foliation of the space-time, which I'm just writing as a Cartesian product here. And then the leaves of these foliation, I assume them to be space-like hypersurfaces. So this means that the leaves of this foliation, if you look at the metric induced on the leaves, it's Riemannian, so it's positive definite. And I'm also assuming them to be Cauchy hypersurfaces, meaning that these surfaces are intersected exactly once by every inextendable time lag curve. This is not so important here in a sense, right? Perhaps the most important assumption here is rather that the mean curvature blows up, right? So the mean curvature, this is the trace of the Weingarten map, if you prefer. And also, I mean, the mean curvature is describing how the volume is expanding locally, right? So this is blowing up as you go towards the Big Bang. You think of the volume as going to zero here, right? And then it's going to expand drastically. So the mean curvature is going to be very big somehow, right? Okay. I'm also going to assume, in this discussion, I'm going to assume the shift vector field to vanish. And this means that the d by dt vector field is perpendicular to the leaves of the foliation. That's what that means. And I'm going to make another assumption, which is sort of related to the assumption of crushing. I'm going to assume that the logarithmic volume density diverges uniformly. So what does this mean? Well, okay, so if you look at each leaf of the foliation, on each leaf you get an induced Riemannian metric, say G bar, and that metric in its turn induces a volume form. So mu G bar, this is the volume form on each leaf here. And then I'm also fixing just a reference metric on M bar. So G bar ref is just a reference metric, and that's the volume form associated with the reference metric. And then this equality here is defining rho, right? So rho, e raised to rho is like the volume density, and you expect the volume density as you go towards the singularity to shrink to zero, right? And so you expect also that the logarithmic volume density should go to minus infinity. It should uniformly go to minus infinity. As you go towards the Big Bang, things shrink down, right? So that's an assumption. In practice, it's connected to the one. So in the framework I'm interested in here, sort of this assumption is essentially going to imply that the mean curvature is blowing up. So in the framework I'm interested in here. Okay, and now, so this is the basic framework. And now, to describe the asymptotics, what are the important objects here? So what are the important objects? So in my experience, something called the expansion normalized Weingarten map, this is the most important object, right? So what's that? So we look now at one leaf of this foliation, and then I'm going to assume the mean curvature to be positive. Well, I mean, it's not much of an assumption if I already assume this, right? So the mean curvature is positive. I look at the Weingarten map. So again, this extrinsic curvature here, considered as a 1-1 tensor field. And then the thing is that if you look now at the Weingarten map, so the trace of the Weingarten map is the mean curvature. The mean curvature is blowing up. So if you want to describe asymptotics here, as you go towards the singularity, looking at the Weingarten map itself is not really reasonable because that's going to blow up. And so you need to expansion normalize this object in order to get some meaningful information. One way to do that is to just naively divide by the mean curvature. So this is going to be an object that has trace 1. It's a 1-1 tensor field on each leaf of the foliation, and it's going to have trace 1. And in my experience, this is really perhaps the most important object if you want to understand the singularity. So I mean, these oscillations that the BKL speak about, that's sort of a chaotic dynamical system for the eigenvalues of this thing, right? And in convergent settings, well, this should converge. And if you look at, I mean, at least most solutions that I know of, this quantity is bounded, and there is no moral reason why it should be bounded at all, right? So this is a remarkable and really central object in trying to understand Big Bang singularities. Okay, fine. So what is now the basic question here? What is it that I'm trying to do? So I showed you already, so lots of previous results, and these previous results, they provide sufficient conditions on initial data on the singularity that guarantee the existence of a development, right? But what I'm interested in here is, can you say something about necessity, right? So what conditions on data on singularity would be necessary? So if this is, I'm turning this thing around now, right? I mean, because, I mean, of course, you can think of all sorts of sufficient conditions that give you developments, but okay, I mean, maybe this list can go on forever, right? I mean, at some point you want to know also what is necessary. Can I approach this question from the other perspective? And that's what I'm trying to do here, right? Okay, but then if you want to do that, of course, you have to impose some assumptions, right? So you have to impose some sort of, what are the minimal assumptions that I get convergent behavior, right? So of course, this in the end will be subjective, what you consider to be the natural minimal assumptions. And so I'm going to list my personal perspective here, right? What I consider to be natural minimal assumptions. So the thing is that, I mean, if you take now the BKL perspective seriously, then the idea is that kinetic terms dominate over potential terms. So time derivatives dominate over spatial derivatives. So if you look at the geometry, what is the natural time derivative of the geometry? Well, the extrinsic curvature somehow, the second fundamental form. This is in some sense naturally a time derivative of the geometry, right? Very naively. On the other hand, it's clear that we have to expansion normalize this thing somehow. And so, I mean, the expansion normalized Weingarten map should really, even from the BKL perspective, be the natural object to focus on, right? As you go towards the singularity, right? And okay, this thing need not converge. In the oscillatory setting, this object does not converge, right? But it's natural here, if you want convergent behavior, that the dominant behavior is convergent, that the dominant objects, like the expansion normalized Weingarten map converges. This would seem to be necessary if you want to say that things are convergent, right? So I think this is sort of unavoidable, I would say, right? And then if you look at the matter fields, it's sort of similar, right? So if you take the scalar field now, again, the time derivative should be most important. So in this case, I'm just taking the future. So you take the future directed unit normal to the leaves of this foliation. Then you have u phi. That's the sort of time derivative in a sense, right? But as always, you have to expansion normalize because the time derivative is going to blow up typically in the direction of the singularity. So you need to expansion normalize. So it's natural to divide by the mean curvature. And then you get this u hat, which is just 1 over theta u. And then you expect this to converge. So that, I think, is also very hard to avoid if you want the dominant behavior to be convergent, right? And then, okay, this equality may seem this is a little bit more technical. So here, this is a consequence of the Hamiltonian constraint. So if you have a foliation here, and then you know that the Einstein equations are satisfied, this is going to imply some so-called constraint equations on the leaves of this foliation, right? And one of them is the so-called Hamiltonian constraint. And this equality follows by dividing the Hamiltonian constraint by the mean curvature squared and taking the limit, right? Of course, to get this result, I need to throw out a few things. So one is the spatial scalar curvature divided by the mean curvature squared. This should go to 0. But okay, that's in line with the BKL perspective that the spatial derivatives should be less important than the time derivatives. There are spatial derivatives of the scalar field appearing in the energy density, again, divided by the mean curvature squared. But again, spatial derivatives should not be important, so you throw them out, right? And then I've also thrown out the potential divided by the mean curvature squared. This should also go to 0. Here, you can actually have potentials so that doesn't happen. So there are potentials which go extremely quickly at infinity, and then the potential will take over and dominate the dynamics completely. That's a different situation. It's not one I'm interested in here, right? Okay, so these are really the basic assumptions. Now, and as far as I'm concerned, they seem to be pretty hard to avoid, right? And so now, right, so now, on the other hand, it turns out it's not quite enough to assume just convergence. I need to have something to work with. I'm going to need to assume convergence with some sort of rate, right? So in practice, I'm going to assume, and also it's sort of convenient in order to express the estimates, not in terms of the limits, I'm actually going to assume, instead of assuming that u hat phi converges, I'm going to assume that u hat squared phi goes to 0. So that's an expansion normalized normal derivative squared of u goes to 0. So I'm going to make that assumption instead. So in practice, I'm going to make this assumption. So the second derivative of phi is going to decay. So here epsilon is some positive number. Rho is this logarithmic volume density, which goes uniformly to minus infinity in the direction of the singularity, right? And I assume this to decay. And L hat u, well, this is some expansion normalized, normal derivative of the expansion normalized Weingarten map, right? So again, as a substitute for convergence, I assume that this decays instead, right? Okay. And I'm a little bit imprecise or very imprecise concerning the norms here. So it depends a little bit. For some of them, you just need some pointwise norm with respect to reference metric. Sometimes you need a pointwise norm with respect to for the derivatives. Yes.
Basic question. Can I see the metric again? Which metric do you actually use? I'm used to seeing Robertson-Walker metrics, right?
I didn't see. Here is just. I don't have a specific line element. I mean, I have. So I'm assuming I have a foliation of the space-time, right? So I mean, you can.
So there's no expansion term in the metric, right? Like in the. Or are you using conformal coordinates already or something? Maybe I missed this.
No.
Okay.
No. I mean, it's just. I mean, so far I'm only assuming this essentially. Metric takes this form. So it's a. So n is the Laps function, is a positive function, and then dt squared and g bar is the metric induced on these things. That's all I'm assuming so far. Okay. Okay, so if you assume this, then the expansion normalized Weingarten map is going to converge to a limit. Let's call it K ring. And it's going to be convenient to assume that the eigenvalues of this thing is distinct. Otherwise, it becomes a bit messy. So I'm going to assume that here. So the eigenvalues here are distinct. Then there's a technical, I mean, if you want to control higher spatial derivatives, you need to control the sort of relative spatial variation of the mean curvature times the Laps function. But this is a bit technical. Let me not go into that, right? Okay, so now you want to understand what are the asymptotics as you go towards the singularity, right? And now, in order to get meaningful limits, you need to expansion normalize, right? Because, as I said, the mean curvature is blowing up and so on and so forth. You need to expansion normalize. For the Weingarten map, I already have the expansion normalized Weingarten map, and I hope that that's going to converge. So that's fine. What are you going to do with the metric, right? So this is perhaps the most subtle issue in all of this, right? What are you going to do with the metric? Because the problem is that the metric is expanding and contracting in anisotropic ways as you go towards the singularity. And it's actually rather nasty, right? And if you want to get the limit, you have to compensate for that anisotropic expansion and contraction, right? So how are you going to do that? Well, the thing is that the expansion normalized Weingarten map is telling you the directions in which things are expanding, contracting, and the speed. And the mean curvature is telling you the amount. So I'm going to take the mean curvature and I'm going to raise it to the expansion normalized Weingarten map. So note here, theta is a positive function, smooth positive function on the leaf, each leaf of the foliation, and I'm raising it to 1,1 tensor field. But that's fine. You can just use the standard exponential function, right? I mean, the standard expansion in the exponential function, right? So this theta raised to k is meaningful, and it's a perfectly fine and smooth 1,1 tensor field, right? And this is how I'm going to rescale. So G bar is, of course, the metric on the leaves, the Riemannian metric on the leaves of the foliation. And then, okay, for the scalar field, it's just the expansion normalized normal derivative. Okay. Okay. Yeah. Oh, maybe I do over here. Okay. So theta. Well, this is, of course, e raised to log theta. Okay. Yes. Log theta, right? Okay. I mean, because it's perfectly fine, it's a 1,1 tensor field. There's no problem, right? You can do this. Okay. And then, so then you have the rescaling of the normal derivative, and then you have to do some sort of rescaling also for the scalar field to get the meaningful limit, right? Okay. And so now the first conclusion is the following. So, okay, this is sort of almost immediate from the assumption, so that's no surprising. So the expansion normalized Weingarten map converges to limit that phi 1, so the expansion normalized normal derivative phi converges to limit. Again, this was sort of more or less part of the assumptions. This requires a little bit more of an effort, but this is actually rather subtle. So here most of the work is really to argue that that this is true, and because this is very, very far from obvious why this rescaling should actually converge to any meaningful limit, right? So that's most of the effort is really into this, right? That's rather subtle, right? But not only do you get these limits also satisfy certain conditions, right? So okay, this is sort of a no-brainer, so to speak, because trace k is 1, so the limit also has trace equals 1. This k ring is symmetric with respect to H ring. This I was actually assuming, so this is not a conclusion. But here, this is a limit of an expansion normalized version of the momentum constraint. And this and proving this is a bit more of an effort also. So everything involving this H ring is I mean, the metric gets much worse, right? But you can prove this as well, that the eigenvalues are distinct, I was sort of assuming. But now there's a fourth condition here appearing. So what is this fourth condition? I need to explain this terminology in order to explain to you what this condition is. So the PAs, these are the eigenvectors of K ring. So these are, so these are smooth functions, so the eigenvalues are distinct. So the eigenvalues are smooth functions on M bar, right? So these PAs are smooth functions. And then the XAs are unit eigenvector fields really corresponding to PAs. So they're well defined up to a sign. There's a minus sign here, of course, which I'm not accounting for. So they're sort of well defined, but not completely. And then given this, so locally at least, you have these nice smooth eigenvector fields. And then you get the structure coefficients associated with that. And they're also well defined up to a sign then, right? In a sense, because the eigenvector fields were well defined up to a sign. But therefore, I just to eliminate all ambiguity, I just square it, and then that doesn't matter how I chose the signs here, right? This is component by component. Yeah. This is component by component. Yeah, exactly. But I mean, in the end, you can reformulate this in very. The essential feature is whether this vanishes or not, and that also doesn't depend on how you choose these eigenvector fields. So it's not really. I mean, you can phrase this in many different ways. So then the point is that if at the point x bar in M bar, if this condition is satisfied, well, the structure coefficients have to vanish in a neighborhood. Right? This is the fourth condition, and this is this additional degree of freedom you have to kill off to avoid oscillations, essentially, right? So this is isolating it, but in a geometric way, right? So the point here. Okay, so what have we gained here? So this is now my suggestion for data on the singularity, right? This is what I would suggest we choose as data on the singularity. So what is the advantage of this notion of data on the singularity? Well, first of all, it's of course covariant, right? So I mean, this is completely geometric. And speaking of, isometry classes of data on the singularity and so on and so forth, this is perfectly fine. There's no complication at all, right? Also, if you take all the examples I gave before, if you take the Anderson and Rendell, their result, so a velocity term dominated, a solution to the velocity term dominated equation can be reinterpreted as a special case of data in this sense. This is a special case. Yes?
This condition 1 plus PA minus PB minus PC is less than or equal to 0. That's a condition on, let's see, largest eigenvalue, right? Because you can add the trace.
Well,
The sum of the PA plus PB plus PC is that 1?
This is now any space-time dimension somehow, right? So for instance, in vacuum, this will always be satisfied somehow. It will always be negative. For instance.
PA, PB, and PC are all eigenvalues of K ring.
It's all eigenvalues, and I should also point out, of course, if B equals C, this always automatically vanishes. So B equals C is uninteresting. And if A equals B, or A equals C, well then since the eigenvalues are distinct, and the sum of the squares equals 1. So from this, the sum of the squares is less than equal to 1, right? So then if A is equal to B or equal to C, this is automatically strictly positive, right? So the only interesting case is when A, B, and C are all distinct. That's the only interesting case. In 3+1 dimensions, then this one says that the eigenvalues sum up to 1. So then this is actually just, if A, B, and C are distinct, this is just 2 times PA.
Yes.
So this corresponds to PA being positive, strictly positive, all the eigenvalues being strictly positive, which is the positive definite condition that Anderson and Randall had. I don't know if I answered your question. I just said about
You answered it to the point.
Okay, yeah.
So this fits with the Klinger conditions? This as well?
Well, I mean, so the thing is that, so as far as I understand, what Fornodavlos and Luke do, they generalize this result. And Fornodavlos and Luke is a special case of this. So, and if you take the result, the Gaudi data is also a special case of this. I mean, all the things I've checked is all special cases of this, right? My expectation is that all the sort of results in the Einstein scale of field setting, this is all special cases of this. This is my expectation, right? So, okay, so that's the advantage. I think that this can be used as a unifying perspective on data on the singularity. This notion is geometric in nature, right? You can also think of it, I mean, so this asymptotically velocity term dominated condition, I mean, the velocity term dominated equations, it's not so clear that they're geometric, and this Jim and Vince already point this out in their article. But I mean, you could say here that, well, if you have a solution that induces initial data in this sense, you could argue that, well, this is a geometric way of saying that the solutions are asymptotically velocity term dominated. Another advantage is that, I mean, if in a given symmetry class you have solutions to this, then you expect the generic behavior to be sort of convergent or quiescent. If there are no data like this, you expect it to be oscillatory. So for instance, in Bianchi 9 vacuum, there are no data like this. So therefore, you would expect that you have oscillatory behavior, and yes, you have oscillatory behavior, right? And then in a very favorable situation, you can hope that you can use these data to parametrize solution. This is, in the dream world. So if you can use these data to parametrize solutions, then the data not only give you as detailed asymptotics as you could possibly hope for, they also label the solutions, right? Okay. Right. Okay. So now, okay, I have a little bit more time, I think. So now I was focused here on necessity, right? So I wrote down some, to my mind, minimal assumptions, and then arrived at this notion of data on the singularity, right? But now you can also ask, what about sufficiency? Now that you have this, if you have data in this sense, are there corresponding developments? So then I want to highlight actually some work of a student of mine, so Andres Franco Grisales. So he posted a paper on Archive a few months ago saying that, yes, there are developments corresponding to data in this sense, right? So if you're given data, initial data on the singularity, and V has to be an admissible potential, so you have to, V is not allowed to grow too fast at infinity, that's essentially the condition. Well then, there is a development, which also has this Gaussian foliation, so that if you look at these expansion normalized quantities for the actual solution to the Einstein nonlinear scalar field equations, they converge to the prescribed data, right? So given data on the singularity, there is a development with this Gaussian foliation and the data, I mean, the expansion normalized version of the data on finite time slices is going to converge to the asymptotic data, right? And this, I should also say, this is in the smooth setting, right? So this result, in that sense, generalizes at the same time both the result of Anderson and Rendel, because that's contained, that's a special case. Okay, there's the issue of the non-degenerate, the distinct eigenvalues, but otherwise it generalizes the result of Anderson and Rendel. At the same time, it generalizes the result of Fornodavlos and Luke, because it's also contained as a special case in here. And in this case, you can actually have data on the singularity where on some part of the singularity, you have behavior like Anderson and Rendel. Some other parts of the singularity, you have vacuum type behavior, like Klinger or von Odovlos loop. That's included here. But this is now existence, right? So, and this, you can formulate it, an alternative statement here is that given initial data on the singularity, there is a locally Gaussian globally hyperbolic development of the data. So, yes. Yes, I'm sorry, I should have said this. So, yeah. So here I am assuming, yeah, that's true. So I'm assuming sigma to be closed. I mean, so in von Odovlos and Luke, they all only look at the case of a 3 torus. Here, sigma is a closed manifold, but closed 3-dimensional manifold.
Can you localize this in time or by domain of dependence?
That might be possible, yes, but I mean, I'm not going to say anything about that. Yeah. I mean, von Odovlos and Luke essentially say in their paper, well, it's easy to localize this, and then I discussed it with them. It turned out it's a little bit more difficult, but I think they can do it in their construction. I mean, it's quite conceivable you could do it here, but it's not done. It's not trivial. I don't think it's trivial. Okay. And so now, what about uniqueness? Well, in some sense, I would claim there's sort of an analog of the Choquet-Brois-Geroch result, a global uniqueness result, right? So given initial data on the singularity and an admissible potential, there's actually maximal locally Gaussian globally hyperbolic development of the data, which is unique up to isometry. So this is sort of an analog of the Yvonne Choquet-Brois, Robert Geroch, uniqueness of maximal global existence and uniqueness of maximal globally hyperbolic development, but for data on the singularity. Right? This is quite nice. So this was a paper of my student. And then, okay, so let me then perhaps wrap up by mentioning some open problems. I mean, so as some of you know, I mean, recently there have been quite a lot of results about stable Big Bang formation. You start at the finite Cauchy hypersurface, you go towards the singularity and get stable Big Bang formation. And in some of these results, at least the asymptotics are somewhat incomplete. And you would like in those results to show that you always get data on the singularity in this sense. That would be nice, but that's an open problem and it might certainly be difficult. If you're starting with data on the singularity, well, then, okay, so Andres' result is actually, I should have said, I don't know if I said, it's in 3+1 dimensions, and for the Einstein nonlinear scalar field equations. But I mean, it's quite natural to expect that you could extend this to higher dimensions, other matter fields, and so on and so forth. So that's a natural open problem. Andres was focusing on the case of Gaussian foliations, but in some settings it might be quite nice to prove that there are nice CMC foliations, right? So that would be quite nice, because a result that I presented a year ago here would then demonstrate that all those solutions would be stable towards the singularity, right? So that would be in some sense. And then it's the final topic, and this is actually originally I was planning on talking mainly on this topic, but now it's left as a remark here at the end. So what would be very interesting is what are the properties of the map from data on the singularity to developments. So you can think that if you look at, you can get a map from isometry classes of data on the singularity to isometry classes of developments. And what are the properties of that map? If you can prove that somehow it's, in some sense, a local diffeomorphism, then that would be very useful, and it would already give you stability automatically somehow. And so, I mean, I've actually spent quite some time recently just sorting this out in excruciating detail in the spatially homogeneous setting to understand how this works out in a special case. And I wanted to describe that, but I don't think I will. So in the spatially homogeneous setting, you can prove that you can give a smooth structure to isometry classes of data on the singularity. You can give a smooth structure to isometry classes of developments. You can prove that the Einstein flow defines naturally a diffeomorphism in some settings between isometry classes of developments and isometry classes of data on the singularity, right? So you get as complete a picture as you could possibly hope for. And then there are some cases, and this I find also rather funny, where you expect a diffeomorphism, but you can prove that isometry classes of data on the singularity have a different topology from isometry classes of development. So of course there cannot be a diffeomorphism. So there must be some exceptional solutions that do not induce data on the singularity. And then you can prove later on that, well, actually there are exactly as many exceptional solutions as you expect somehow, right? So just from a topological observations on the isometry classes of data on the singularity and on isometry classes of developments, you get conclusions concerning the dynamics, which I find rather amusing. But I've spoken enough. So congratulations, Piotr.